G'day chemists, in this lesson we're going to talk about Bohr's model of the atom. We're going to talk about what he thought an atom was, as well as the evidence for it and sort of how he kind of got there. So by the end of this, you should be able to explain to your teacher what Bohr's model of the atom is, as well as apply some basic stuff like electron configuration and describe where electrons are going to be. Electrons are kind of the key to his model of the atom. You should also be able to provide a bit of evidence for it. So this is our vocabulary. I want you to pause the video, write this down, and just have these to refer to when we come back to it as we're going along. So just here, we have a rather excessive model of Bohr's atom, right? It's pretty full on, it's got everything on there. But we need to know that Bohr's model contains the protons and neutrons in the nucleus. The nucleus itself is orbited by the electrons in discrete energy levels called electron shells. Now those discrete energy levels, what that means is that an electron can either be in shell 1, shell 2, shell 3, or shell K, shell L, shell M, but it cannot be in between. So this is where we start to get to quantum mechanics. It cannot exist between those values. It can only exist at those values. The inner shells we call core shells, and the outer shell is the one we call the valence shell. And that's actually the shell which is in charge of the majority of the chemistry that we'll talk about. So the electron configuration, we write that by running the number of electrons in each shell separated by a comma. So for example, if we're talking about atom number 6, which is carbon, it would be 2, 4, because there's 2 electrons in the K shell and 4 electrons in the L shell. So shells are known as we said, K for the first, L, M, N, and there's a maximum number of 2, 8, 18, and 32 in those shells. And this is just another table summarizing it. Make sure we get this table down, as well as this diagram here. So let's talk about absorbing energy, right? How Bohr's model, it took account of the way atoms interact with energy, heat, light, as they pass through them or near them. So as each electron has a discrete energy level, electrons absorb energy and can move up levels, right? And we see that here. Here the electron, well, this is post that this electron here absorbs energy and moves up. And as they lose that energy, because they become unstable, they use the energy moving up, so then they fall back down. It's like throwing a ball up. You put energy in to launch it higher, and then the ball comes back down. And as it comes back down, they emit the excess energy. That's what's going on here. So we can see the energy being emitted, sent away. And that's emitted as a photon, or light, so a light particle. So this gives us emission spectra. Now, due to each element having its own pattern of electrons, so each element has, carbon has 6 electrons, and carbon always has 6 electrons. Well, unless it's an ion. But a carbon element has 6 electrons. An oxygen element has 8 electrons, and so forth. Because of this, we get a distinct pattern of photons. Now, this pattern of photons is called an emission spectra. Absorption spectra, that's what we call it if we've got a gas, like just here, and we pass energy through it. As we pass energy through those gases, what they will do is they will absorb energy. They'll absorb the energy going through, but they'll absorb it at those particular energy levels, like those particular electrons. And as those electrons move up, that energy is absorbed, and all the light goes through except the absorption lines. So we get emission lines, and each one of these is a specific photon related to an energy movement of electrons, and these absorption lines, are specific to each electron moving a certain amount as it absorbs the energy. This absorption spectra is the inverse of the emission spectra, and we can use these to identify specific elements. As I said, each element has its own particular one. Helium, for example, was first identified using emission spectra as it was coming out of the sun, which is kind of awesome. As I said, these are due to individual patterns of electrons in the elements. Hope that made a lot of sense. If you have any questions, put them in the comments below. Make sure to subscribe so you can keep up with everything we're doing here. And yeah, we'll see you next time. Thanks for watching. Bye now.